Hello everyone, this is lecture 3 where we're going to talk about important op-amp applications. Two of those would be summing and differential amplifiers. A summing amplifier has two or more inputs and its output voltage is proportional to the negative of the algebraic sum of its input voltages. A two-input summing amplifier is shown in figure 13-20, but many number of inputs can be used. The operation of the circuit and derivation of the output expressions are as follows. Two voltages VIN1 and VIN2 are applied to the inputs and produce currents I1 and I2 as shown. Using the concept of infinite input impedance and virtual ground, you can determine that the inverting input of the op-amp is approximately 0 volts and has no current through it. This means that both input currents I1 and I2 combine at the summing point A and form a total current IT, which goes through a feedback resistor RF, as indicated in figure 13-20. Let's pay attention to this figure once again. We have a node A here, and if we apply Kirchhoff current law to this node, sum of the currents, which are I1 and I2 that flows into this node, must be equal to the sum of the currents flowing out. One of the currents flowing out is IT, another one is the current flowing into the op-amp. However, since the input impedance of op-amp is extremely high, this current will be practically zero, and there will be no voltage drop between inverting and non-inverting terminal, so we can say that the inverting terminal is at virtual zero, virtual ground. In this case, sum of the currents I1 and I2 must be equal to IT, and that's why we have this expression here. If we apply Kirchhoff voltage law around the output loop, which includes Vout and voltage drop across resistor RF, then starting from ground we will have Vout plus RF IT reaching starting point. So the sum of those two voltage drops must be equal to 0. This equation shows us that. So Vout plus IT RF must be equal to 0. If we substitute IT here with the sum that we already achieved by applying Kirchhoff current law at node A, you will get expression for the output voltage as a function of the sum of two currents. Using a fact that the non-inverting terminal is at 0 point, virtual ground, it appears that the VIN input voltage, which is voltage between this point, input point, and the common, is actually voltage drop across R1. We can use Ohm's law to find the current that flows through this resistor. It's a voltage drop across the resistor divided by value of the resistor. If we now apply substitution in these final expressions for Vout, you will get, instead of I1, you will get VIN over R1. Instead of I2, you will have VIN2 divided by R2, multiply with the feedback resistor RF. If all three resistors here are equal, R1 equals R2 equals RF, then the final expression for the output voltage becomes simply a sum of two input voltages, VIN and VIN2. The previous equation shows that the output voltage has the same magnitude as the sum of the two input voltages, but with the negative sign indicating inversion. Now if you look at the figure 13-21, you will notice that instead of two inputs, we have a summing amplifier with three inputs, V1, V2, and V3. All resistors, input resistors, are already assumed to be identical, RIN, and we have RF as a feedback resistor between output and the input. Derivation of the output voltage is pretty much the same. We will apply Kirchhoff current law first to this node designated here as X, which tell us that the sum of all three currents must be equal to the sum of the currents flowing out. With the assumption that the input current into the op-amp is 0, you are getting expression for the total IF current, which is sum of all three. Now again, applying Kirchhoff voltage law to the output loop, we get Vout plus RF IF to be equal to 0. That's the second expression here. You can solve this expression for Vout, getting negative RF IF, and then IF can be substituted with the sum of all three input currents. Using now Ohm's law, you will substitute the value of these currents to become a function of the input voltage. So I1 equal V1 over R IN, and I2 will be equal V2 over R IN, and I3 will be equal to V3 over R IN. Once again, if RF is equal to RIN, this output becomes a simple sum of all three input voltages. A general expression is given in equation 13-4 for a unity gain summing amplifier with n inputs, as shown in figure 13-21, where all resistors are assumed to be equal in value. In this case, Vout becomes a sum of all input voltages from 1 to lowercase n. Negative sign indicates inversion because we are using non-inverting configuration for this application. Few words about averaging amplifier. A summing amplifier can be made to produce a mathematical average of the input voltages. This is done by setting the ratio RF, feedback resistor, over R, input resistance, equal to the reciprocal of the number of inputs, call it lowercase n. So if RF over R is equal 1 over n, then we can convert simple summing amplifier into the averaging amplifier. You obtain the average of several numbers by first adding the number and then dividing by the quantity of the numbers you have. Examination of equation 13-5 and a little thought will convince you that the summing amplifier can be designed to do this. The next example will illustrate it. In this example, we will show that the amplifier in figure 13-24 produces an output whose magnitude is the mathematical average of the input voltages. If you look at this figure, you will see that we have 4 inputs, that we have all input resistors being equal, 100 kilo ohms, and that the feedback resistor is 25. If you find the ratio RF over R, you will find that it's 1 over 4, and 4 matches the number of the inputs. This calculation is straightforward, giving us the final result of negative 2.5 volts. If you try to find numerical value for the average value of the input signals, you sum values of all members of the sum, you divide with the total number of members, and you will get 2.5. Of course, the magnitude is the same, it's just that the negative sign indicates inversion. If you want to get a positive value for the average value, you will have to put in series one inverting configuration of op-amp with a gain of 1. So when the input is negative 2.5, the output of this inverting amplifier will give you positive value of 2.5 volts. So you will then match even the sign. So you can ask yourself, how can we use summing amplifier? What would be a typical application? If you look at the figure 13-22, you will see the application of a summing amplifier as the audio mixer. If the input resistances of a summing amplifier are connected to potentiometers, the individual input signals can be mixed together by varying amounts. For instance, channel 1 can have one level, channel 2 can have an independent level as well, and the third channel can also have a different level. So our V1, V2, and V3 can have a different amplitudes value at the input of the summing amplifier. If the RF feedback resistor is a variable in the form of a potentiometer, you can change overall gain of some signals at the output. For example, measuring temperature, you can add a negative offset voltage to make the output voltage or display read 0 at the freezing point, or you can produce an audio mixer for editing or mixing together individual waveforms like sounds or video signals from different source channels, vocals, instruments, and so on, before sending them combined to an audio amplifier. Another useful application of a summing amplifier is a weighted sum digital to analog converter. If the input resistors RIN of the summing amplifier double in value for each input, for example 1K, 2K, 4, 8, and 16K, and so on, then a digital logical voltage, either a logical level 0 or a logical level 1 on these inputs, will produce an output which is a weighted sum of the digital inputs. Consider the circuit below, which represents typical digital to analog converter. We have a network of resistors which are following binary distribution, so R1 is 1K and R4 going all the way to the 8K. In a case of the 4-bit word, they constitute input resistors for the summing amplifier. So that means that each of those inputs will contribute differently to the output, to the analog value. Of course, this is a simple example. In this DAC summing amplifier circuit, the number of individual bits that make up to the input data is only 4 bits, but it will ultimately determine the output step voltage as a percentage of the full scale of the analog output voltage. Practically, what that means is when I have a different logical levels will have a different contribution to the output, and I will have unique analog value. If I have, for instance, all zeros, all bits are here sent, for, let's say, from microcontroller to be 0, I will have a minimum output voltage. If I have all ones at the input, that means that I will have a maximum analog output voltage, whatever this maximum value can be. Digital to analog converters as well as analog to digital converters are much deeper explored in our Electronics 3 course ETEC201. Differential amplifiers. Thus far, we have used only one of the operational amplifier's inputs to connect to the amplifier, using either the inverting or the non-inverting input terminal to amplify a single input signal with the other input being connected to ground. But as a standard operational amplifier has two inputs, inverting and non-inverting, we can also connect signals to both of these inputs at the same time, producing another common type of operational amplifier circuit called a differential amplifier, or sometimes called difference amplifier. As we learned earlier about operational amplifiers, all op-amps are differential amplifiers due to their input configuration. But by connecting one voltage signal onto the input signal and another voltage signal onto the other input terminal, the resultant output voltage will be proportional to the difference between the two input voltage signals of V1 and V2, as shown in figure 13-24. Let me see whether we can derive the expression for the output voltage of the differential amplifier configuration as shown below in figure 13-25 again. The good thing about this configuration is that we can consider it as a linear network, and the superposition theorem in this case applies. So we can find the output voltage by individually evaluating the output portions of each of those signals acting alone in a circuit. So in the first case, when V2 is equal to 0, so we will ground a voltage V2, there will be only one V1 acting in a circuit, and in this case you can easily recognize inverting configuration. The gain of the inverting amplifier is RF over RI, here in this case R3 over R1, so the output voltage that will exist when only V1 is acting in a circuit will be gain R3 over R1 times the input voltage V1. That will be the part, call it A, of the output voltage due to V1. To find the second part, we will ground V1. so it becomes 0, and then there will be only V2 acting in a circuit. In this case, signal is brought to the non-inverting amplifier, and the gain of the non-inverting amplifier applies. We know that the gain of the non-inverting amplifier is 1 plus RF over RI, and this ratio is 1 plus RF over RI, a gain of the non-inverting amplifier. Non-inverting amplifier amplifies the input on the non-inverting terminal, but this is not V2. Actual voltage VB that exists at the non-inverting input is given with the voltage divider R4, R2, so VB is given with this expression. The overall contribution of the second voltage to the output will be input VB times gain of the non-inverting amplifier. Now we can evaluate total output voltage by making algebraic sum. B part belongs to the non-inverting input, and it will have a positive sign, while the second part will have a negative sign because we are dealing with the inverting amplifier. So when we sum all those individual parts to find overall output gain, it becomes a fairly complex transfer function. When resistors R1 and R2 are equal, and R3 and R4, you can simplify this complex expression, so it becomes expression highlighted in yellow. R3 over R1 multiply difference between two input voltages V2 and V1. If all the resistors are of the same ohmic value, that is R1 equals R2 equals R3 and equals R4, then the circuit will become a unity gain differential amplifier, and the voltage gain of the amplifier will be exactly 1 or unity. Then the output expression would simply be Vout equals V2 minus V1. Also note that if input V1 is higher than the input V2, so V1 is higher than V2, the output voltage sum will be negative. And if V2 is higher than V1, the output voltage sum will be positive. The differential amplifier circuit is very useful op-amp circuit, and by adding more resistors in parallel with the input resistors R1 and R3, the resultant circuit can be made to either add or subtract the voltages applied to their respective inputs. One of the most common ways of doing this is to connect a resistive bridge, commonly called a Wheatstone bridge, to the input of the amplifier as shown below. A lot of sensors are coming in a form of resistive bridge, and in this case such a configuration will be used to amplify the difference between different branches of resistive bridge. One major limitation of this type of amplifier design is that its input impedances are lower compared to that of other operational amplifier configurations. For example, a non-inverting single-ended input amplifier. Each input voltage source has to drive current through an input impedance, which has less overall impedance than that of the op-amp's input alone. This may be good for a low impedance source, such as the bridge circuit given earlier, but not so good for a high impedance source. And let's take a closer look what that means. For instance, if V1 is a real source connected to the inverting terminal, this source will see input impedance of ZIN1 approximately equal to R1, if you remember our expression for the input impedance. A source V2, which is connected to the non-inverting terminal, sees input impedance of ZIN2, which is series combination of R2 and R4. Now, if all resistors are equal, let's say, so ZIN1 is equal to R and ZIN2 is equal to 2R. Therefore, even in the case of identical source amplitudes, the difference will be formed by input voltage dividers. The input voltage dividers, which are consisted of a source in resistances and input impedances. we will face very serious issue that voltages which are identical, V1 and V2, that have no difference whatsoever, we expect to have the output. However, when you connect it to the circuit like this, you will find out that there will be a difference between them, and because of that, there will be some output. One way to overcome this problem is to add a unity gain buffer amplifier, such as the voltage follower that we described earlier, to each input resistor. This then gives us a differential amplifier circuit with the very high input impedance and very low output impedance, as it consists of two non-inverting buffers and one differential amplifier. This then forms the basis for the most of instrumentation amplifiers. An instrumentation amplifier is a differential voltage gain device that amplifies the difference between the voltages existing at its two input terminals. The main purpose of an instrumentation amplifier is to amplify small signals that may be riding on a large common mode voltages. The key characteristics are high input impedance, high common mode rejection, low output offset, and low output impedance. The basic instrumentation amplifier is an integrated circuit that internally has three operational amplifiers and several resistors. The voltage gain is usually set with external resistors, as we will see soon. A basic instrumentation amplifier is shown in figure 14-1. The op-amps A1 and A2 are non-inverting configuration that provide high input impedance and voltage gain. The op-amp A3 is used as a unity gain differential amplifier with high precision resistors that are all equal in value. So R3 and R4 are equal. So once again, when you look at the structure of the instrumentational amplifier, you will recognize two voltage followers and one typical differential amplifier that we described before. We know how the voltage follower operates and what are characteristics, and we know how differential amplifier operates. So we can explore the property of the instrumentational amplifier. As I said before, sometimes the gain of the instrumentational amplifier can be controlled by introducing either external or internal resistor RG, and setting up different values, we can provide different voltage gains of the instrumentational amplifier. Once again, we cannot expect any voltage gain from amplifier A3, which works in differential configuration, because resistors R3 and R4 are equal. So whatever is the Vout1 and Vout2 at the input of this differential amplifier, the output will be a difference between the two. The overall voltage gain of the instrumentational amplifier can be defined as ratio Vout over differential input V2 minus V1, as it's given in equation 13-1. If we look now at the figure 14-2a, we will identify certain currents and voltage correlations which will help us in derivation of this voltage gain in terms of individual voltage gains of each of the stages in the instrumentational amplifier. So if you look at the A1 input, you will see that the V1 is connected to the non-inverting input, and inverting input is designated as VA. If the assumption that the difference between those two potentials must always be very, very small, close to zero, that means that VA will be practically equal to V1. The same story is valid for the voltage follower A2. VB will be very, very close in value with V2. Another assumption is that the input current into the high impedance voltage follower will be approximately be equal to zero. This is valid for voltage follower A1 and for voltage follower A2 as well. If this is true, then the current that flows from the output of the A2 follower to the output of the A1 follower will be the same. How we can verify that? Look at the Kirchhoff current law applied to this node. Current that flows in, which is designated as Ix, must be equal to the sum of the currents that flow through the resistor Rg and to the input of the voltage follower A2. Since we already assumed that this current is very small, then we can neglect this part, so the current through Rg becomes Ix. The similar application of the Kirchhoff current law to this node will tell us that the current that flows in, being Ix, must be equal to the sum of the currents flowing out. Since I is already assumed to be 0, then the current through R1 must be equal to Ix. So we will keep those two assumptions as we proceed with the analysis and derivation of voltage gain for instrumentational amplifier. When R3 is equal to R1, we saw earlier that the voltage gain of the differential amplifier A3 becomes 1, and therefore the output voltage is given as a difference between two input voltages of that differential amplifier, and those are Vout2 and Vout1 as shown in equation 13-3. That means that the original definition of the output voltage of instrumentation amplifier Vout over difference between two inputs, V2 and V1, becomes Vout2 minus Vout1 divided by V2 minus V1. Now we will repeat once again analysis and assumptions that we presented in the previous slide. A careful inspection of the circuit in figure 14-3 reveals two important facts. First, due to a small differential voltage Vd, practically equal to 0, at both inputs of the op-amps A1 and A2 voltage followers, potentials at both sides of the resistor Rg becomes Vi close to V1 and Vb close to V2. Very high impedances of both op-amps A1 and A2 makes currents II close to 0. So the same current Ix must flow through resistors R1, R2 and Rg. Now we can use Ohm's law to find the voltage drops across resistors R1 and R2 as follows. So look at the picture 14-3 to easily identify voltage drop across resistor R2. On one side we have Vout2, on the other side of the resistor we have V2, because we said Vb is close to V2. So that means that the voltage drop across this resistor will be Vout2 minus V2 must be equal to the product of the current that flows through the resistor R2Ix. If we apply the same Ohm's law across resistor R1, voltage drop will be V1 minus Vout1, so this difference is equal to the product of R1 times Ix. Typically R1 and R2 are equal, so when we apply addition to those two equations, the result becomes equation 13-3. We are summing left-hand sides and right-hand sides, and they are all given in equation 13-3. Now if we substitute the current through Rg using Ohm's law again, which is given in equation 13-4, and we will repeat it once again by looking into the figure 14-3, on one side of the resistor Rg we have V2 potentials, on the other side is V1 potential, so voltage drop will be V2 minus V1 divided with resistor Rg will give us current that flows through it. If we substitute the value for Ix in equation 13-14, which is repeated here, you will get equation 13-15, which is regrouped by having common term V2 minus V1, and then what's left in the bracket is 1 plus 2R over Rg. Now we can express total voltage gain of the instrumentation amplifier as Vout minus Vout1 over V2 minus V1 becomes 1 plus 2R Rg as given in equation 13-6. This derivation is different from the textbook derivation of the instrumentation amplifier gain, which, although not quite obvious, utilize superposition theorem applied to both buffer amplifiers A1 and A2. According to this approach, the output voltage of the A1 amplifier Vout1 is produced by two input sources, V1 and V2. Again, keep in mind that VA is close to V1 and VB is close to V2. In this case, the input source V1 acting alone when V2 is grounded, that means VB is grounded, is connected to non-inverting input of the A1 and experience amplification of 1 plus R1 over Rg. Remember, for non-inverting configuration, 1 plus Rf over Ri is the voltage gain. Source V2, when we're acting alone, that means that V1 becomes grounded. In other words, VA will be grounded as well, so the input is brought to the VB. We are dealing with the inverting configuration. An amplifier, A1, is acting as inverting amplifier having a gain of negative R1 over Rg. Applying superposition theorem, the total output voltage Vout must be algebraic sum of those two actions. So Vout1 is be given with the equation 13-7. By analogy, the output voltage of A2 amplifier Vout2, that's the output of the second amplifier, Vout2, is produced by two independent input sources, V2 and V1 again. In this case, the input source V2 acting alone with V1 being grounded is connected to the non-inverting input of the A2 and experience amplification of 1 plus R2, which is Rf, over Rg, which is Ri. Once again, V1 is grounded, that means that VA is at ground potential. Source V1, when acting alone, so V2 being grounded, that means VB is grounded, is connected to inverting input, that's VA, and therefore sees amplifier A2 as an inverting amplifier having a gain of negative R2 over Rg, that means Rf over Ri. Applying superposition theorem, the total output voltage Vout2 must be algebraic sum of those two actions, which is written here as equation 13-7. So here is the part due to V2 acting alone, here is another part due to V1. Now we can form V output as a difference between Vout2 and Vout1, and when we substitute found value for Vout2 and Vout1, we will get equation 13-18. Typically we said that R1 is equal to R2, so this last equation 13-8 becomes 1 plus 2 R over Rg times difference between two input signals V2 minus V1, as given in equation 13-9. Now we can finally evaluate the overall voltage gain of the instrumentation amplifier as a ratio of Vout2 minus Vout1 divided with V2 minus V1, which is directly given by equation 13-9 as 1 plus 2R over Rg. The external gain setting resistor Rg can be calculated for the desired voltage gain by solving this expression 13-10 by Rg. So it will be 2R over closed loop gain minus 1. So whenever there is a need to calculate which resistor will give us required gain, we can apply equation 13-11 to do the calculation. Instrumentation amplifiers in which the gain is set to specific values using a binary input instead of a resistor are also available. Here in example 14-1, we will determining the value of the external gain setting resistor Rg for the certain IC instrumentation amplifier with R1 that R2 equal 25 kilo ohms. The closed loop voltage gain, that means required gain, will be 500. Direct application of the previous expression will give us a value of 100 ohms. So when we have instrumentational amplifier that requires a gain of 500 and has internal resistors R1 and R2 set to 25 kilo ohms, we will need RG external resistor to be 100 ohms. The instrumentation amplifier is normally used to measure small differential signal voltages that are superimposed on a common mode voltage, often much larger than the signal voltage. Applications include situations where a quantity is sensed by a remote device, such as a temperature or pressure-sensitive transducer, and the resulting small electrical signal is sent over a long line subject to electrical noise that produces common mode voltages in the line. The instrumentation amplifier at the end of the line must amplify the small signal from the remote sensor and reject the large common mode voltage, as illustrated in figure 14-3. Now here on the left hand side we have illustration of the small differential high frequency signal riding on a larger low frequency common mode signal. When these two signals are brought to the input of the instrumentation amplifier, we expect that a difference between voltages in point 1 and 2 will be amplified, while the common mode signal, this large low frequency signal, will be equal on both inputs, and because there is no difference between them, they will not be amplified at all. And as you can see, the output will give us amplified differential signal, but there will be no common mode signal. So from this complex and blurry signal, where the useful signal is actually very, very small, we are getting only useful signal at the output. Now that you have the basic idea of how the instrumentation amplifier works, let's look at the specific device. A representative device from the manufacturer analog devices could be AD622, as shown in the figure 14-4, where integrated circuit pin numbers are given for reference. This instrumentation amplifier is based on the design using 3 op-amps that was earlier shown in figure 14-1. So if you look at the figure, if you look at the symbol of AD622, you will recognize power supply connection, plus and minus. You will recognize the output. Pin 5 will be reference point, common, not necessarily connected to ground. Pins 3 and 2 will designate input points for the differential signal, and you will have pins 1 and 8 where external RG resistor for setting up the gain could be connected. Some of the features of the AD622 are as follows. The voltage gain can be adjusted from 2 to 1000 with external resistor RG. There is a unity gain with no external resistors. If there is no resistor connected between pins 1 and 8, the gain will be 1. The input impedance is, as you can see, very high, 10 gigaohms. The common mode rejection ratio, CMRR, has a minimum value of 66 dB. Recall that a higher CMRR means better rejection of common mode signals. The AD622 has a bandwidth of 800 kHz when the gain is set up to 10, and the slew rate is 1.2 volts per microsecond. You can see here, if you have a low voltage gain, then the bandwidth is fairly large. However, if you keep on increasing that, we are shrinking the bandwidth, and for instance at the 100 voltage gain level, it will be only a few kilohertz. For the AD622, an external resistor must be used to achieve a voltage gain greater than unity. As indicated in figure 14-5, resistor RG is connected between RG terminals pin 1 and 8. We already said that no resistor is required for unity gain. RG is selected for the desired gain based on the following formula: 50.5 kilo ohms over required voltage gain minus 1. Pay attention, this specific value of the resistance that you might find in formula supplied by manufacturer is related to 2R value of resistors R1 and R2 in a 3 op-amp configuration. This is a value of 2R, so that means that each resistor has a half of that value. Now different designs and different manufacturers will have a different values. You have to look at the data sheets to know exactly what those values are and how to calculate RG. And here is example 14-2, where we have to calculate the voltage gain and determine the bandwidth using the graph in figure 14-6 for the instrumentation amplifier in figure 14-7. We see from the figure that RG is set to 510 ohms. In this case, applying formula supplied by manufacturer to calculate the gain will be 50.5 kiloohms over the value of RG, which in this case will be 100. Looking now back into the figure 14-6, where I presented the gain versus frequency, for the given value of 100 gain, you can estimate the bandwidth to be around 80 kilohertz. Various types of transducers are used to sense temperature, strain, pressure, and other parameters in many types of applications. Instrumentation amplifiers are generally used to process the small voltages produced by a transducer, and often they are used in noisy industrial environments where long cables connect the transducer output to the amplifier inputs. Noise in the form of a common mode signals picked up from the external sources can be minimized but not totally eliminated by using coaxial cable in which the differential signal wires are surrounded by a metal mesh sheathing called a shield. As you know, in an electrically noisy environment, any common mode signals that are induced on the signal lines are rejected because both inputs to the amplifier have the same common mode signals. However, when a shielded cable is used, there are stray capacitances distributed along its length between each signal line and the shield. The differences in these stray capacitances, particularly at higher frequencies, result in a phase shift between the two common mode signals, as illustrated in figure 14-8. The result is degradation in the common mode rejection of the amplifier because the two signals are no longer in phase and do not completely cancel. Differential voltage is created at the amplifier inputs. Now, if those two stray capacitances are different for those different lines, on a high frequency they create a phase shift and common mode signals will not be in phase anymore. So their difference is not zero anymore. There will be some difference which will be amplified by instrumentational amplifier who is amplifying the difference at the input. Guarding is a technique to reduce the effect of noise on the common mode operation of an instrumentation amplifier operating in a critical environment by connecting the common mode voltage to the shield of coaxial cable. The common mode signal is fed back to the shield by a voltage follower stage as shown in figure 14-9. The purpose is to eliminate voltage differences between the signal lines and the shield, virtually eliminating leakage currents and cancelling the effect of the distributing capacitances so that the common mode voltages are the same in both lines. So as you can see, the idea here is to eliminate or minimize this effect of shielding is that this shield is not grounded anymore. It is actually connected to the common mode point of the instrumentation amplifier. So the voltage follower, as you can see, output, this is a gain of 1, the same potential brings here. Because now this is not the ground, there will be no leakage current flowing through these stray capacitances, and we are practically cancelling this effect. The voltage follower is a low impedance source that drives the common mode signal onto the shield to eliminate the voltage difference between the signal lines and the shield. When the voltage between each signal line and the shield is 0, the leakage currents are also 0, and the capacitive reactances become infinitely large. An infinite large XC implies a 0 capacitance. On the market, you can find instrumentation amplifier which can already provide this effect with the voltage follower, and this feature is called data guard. Most instrumentation amplifiers can be configured externally to provide a shield guard driver, but certain integrated circuit like AD522 amplifiers, however, provide an internally generated guard output that is intended for very critical environments. This example is shown in figure 14-10, which is a precision integrated circuit instrumentation amplifier designed for applications requiring high accuracy under worst-case operating conditions and with very small signals. The pin labeled data guard is the shield guard output. So the monolithic integrated circuit already includes this voltage follower that we use to connect the shield to the common mode signal of the instrumentation amplifier. Few words about lab exercises. All experiments in lab exercise 12 are conducted on printed circuit board PCB number 8 from the ETEC201 lab trainer set. Before attempting to do actual experiment, take some time to familiarize yourself with this board. Here is the schematic of this board number 8, and you can easily identify two circuits. Circuit 8.1 will be a summing application, and circuit 8-2 will represent differential amplifier. Now if you look at the circuit 8.1, you see that the inputs VS1 and VS2 are brought from the two channels of the function generators via AC signal distribution switch S2. So using this switch you can either connect those two channels to the circuit 8.1 or 8.2. You will bring different signals to the inputs and you will try to evaluate their sum. If there is any need to adjust the output 0 when the input is equal to 0 to eliminate the offset, you will have a potentiometer here on both circuits, pot 1.1 and pot 2.1. When it comes to the differential amplifier application, you also have two inputs that are coming from the function generators, and setting up a different type of the inputs, you will evaluate how differential amplifier operates. Here is the overall look of that board, and you will be able to identify once again power switch S1, 3 banana connectors for power supply connection. There are two channels of the function generator here. Switch S2 defines which way those two channels will go, either towards circuit 1 or towards circuit 2. When you switch to circuit 8.1, those two signals will be at the test point 12 and 11 as VS1 and VS2. So you will combine them, find the sum, and evaluate the output using oscilloscope. If your switch S2 is set to circuit 2.2, then the function generator signals will be brought here at test point TP22 and TP21 as VS1 and VS2 signal sources respectively. So you will bring different voltages at the input and you will evaluate their difference at the output TP23. Pay attention, there is a small switch here which can bypass resistor of 1K or leave it in a circuit, in this feedback circuit. This one will introduce artificially mismatch between resistors, so you will be able to explore what that means if those four resistors are not identical as required by a perfect differential amplifier operation. To illustrate a very interesting property of a differential amplifier, I prepared two very interesting and very exciting experiments. On the top snapshot of the oscilloscope screen, you will see a complex signal consisted of the high-frequency useful signal and the low-frequency interference signal, typically 60 Hz or 50 Hz. Now, any attempt of a regular amplifier to amplify this complex signal shown at the top trace will end up amplifying both signals, interference and useful signals. However, a differential amplifier can do a miracle here, as I hope you will witness. If the interference signal appears as a common mode signal on both inputs, then it will be multiplied by a very small common mode gain, while the useful signal, being a difference, will be multiplied with a huge differential gain, and the output will appear clean useful signal only. On the bottom, there is even more interesting case where the high frequency noise been superimposed on the useful low frequency signal. Again, any attempt to amplify such complex form will end up amplifying both signals. However, if this noise, which is shown at the bottom trace, appears as a common mode, it will be suppressed at the output, and the difference between those two signals, which is a useful signal, will be multiplied by a huge differential gain, and it will appear at the output more or less clean. Those two signals are very common in practice. However, it's very hard to create them in controlled environment like our labs. So that's why I had to program our function generator and create arbitrary waveforms shown here. This is a very tricky experiment, and you really have to follow instructions from lab manual very, very carefully to be successful in witnessing how superior the differential amplifier actually is. And this will conclude lecture 3, summing and differential amplifiers. Thank you.